All right, welcome. Today we're going to peel back the curtain on artificial intelligence. We're going to look at the digital brains that power, well, so much of our modern world. I'm talking about artificial neural networks. Let's get right into it. Have you ever really stopped to wonder how your phone unlocks with just a glance? Or how some AI can create this incredible art from just a few words you type? It honestly feels like magic, right? But it's not. The secret behind all of it is this really powerful tool, and it's actually inspired by the human brain itself. It's called the Artificial Neural Network, or ANN for short, and that's exactly what we're going to unpack together today. Okay, so first things first. Before we get into the nitty-gritty, let's get our bearings. You hear all these terms, AI, machine learning. So where do neural networks fit into this whole big picture? Well, it all starts with the biggest umbrella term, artificial intelligence, or AI. I mean, this is the entire huge field of trying to make systems that can do tasks that normally require human intelligence. Now, nested inside of that, you've got machine learning. And this is where it starts to get really cool. See, instead of a programmer writing explicit rules for every single possibility, we just feed the computer a whole bunch of data and let it figure out the patterns on its own. It literally learns from experience. And then, if we zoom in even further, we find deep learning. This is a special type of machine learning that's behind all the huge breakthroughs you hear about. And what makes it deep? Well, it's all about using those artificial neural networks we keep talking about, specifically ones with tons and tons of layers. So you can kind of see it like a set of Russian nesting dolls, right? You've got AI on the outside, then you open it up to find machine learning, then deep learning inside that. And right at the very, very center, the thing that makes all the advanced stuff work, that's where you find the artificial neural networks. They are the engine driving all of this. Okay, so that's all the theory. But, theory is one thing. To really get this, we need to see it in action. So let's give our network a mission. We're going to solve a problem for a local animal shelter. So here's the deal. The shelter needs an AI that can automatically classify animals based on their features. Our job? Let's build a neural network that can tell them if they're looking at a dog, a cat, or a rabbit. So this is what we're working with. On one side, we have the inputs. These are the features of the animal, things like its fur length, the shape of its ears, its weight, what sound it makes. And the network's job is to take all that in and give us one of three outputs: dog, cat, or rabbit. Simple as that. All right, mission accepted. But how do we actually build this digital brain from scratch? Let's take a look at the anatomy of a network. The whole idea, like we said, comes straight from the human brain, right? In our heads, we have neurons firing electrical signals across connections called synapses. Well, in an artificial network, you have nodes, which are basically artificial neurons, and they pass numerical values across their connections. It's a really neat parallel. And here's how that translation from biology to math really looks. The brain's neurons, in the network, those are just nodes. The synapses connecting them, we call those weighted connections, or edges. And that incredible, mysterious process of learning in our brains, in the network, it's a mathematical process of updating those weights. It's all about the numbers. So let's talk about the actual building blocks. You've got nodes. Think of them as the neurons. They just hold a number. Then you have the edges, which are the connections that pass information along. And this is the important part, the weights. A weight is just a number that tells you how strong a connection is. A big positive weight is like shouting, yes, this is super important, while a big negative weight is like saying, nope, ignore this. And all these nodes are just organized into layers: an input layer, some hidden layers in the middle, and an output layer. Okay, so we have the parts, we've put them together. Now for the moment of truth. Let's feed our brand new network some data about an animal and see what it guesses. This first run-through is called the forward pass. Okay, here we go. Step 1. The features of our animal, long fur, floppy ears, go into the input layer. Step 2. That information just ripples through the hidden layers. Each little node takes in the signals, multiplies them by their weights, does a tiny bit of math, and decides whether to fire and pass the signal on. And finally, step 3, the output layer gives us its prediction. It confidently shouts, dog! Except it was a rabbit. Oops. And right there, that's the most important part of this whole thing. The network got it wrong. So the big question is, how does it learn? How does a bunch of math and numbers actually learn from a mistake? Well, it learns using a really clever process called backpropagation. And to make this super clear, forget about computers for a second. We're going to use an analogy that I think makes this click instantly. Learning archery. Yeah, backpropagation sounds complicated, but it's really just a fancy name for learning by working backward from your mistake. Think about it. It's exactly what an archer does when they're trying to hit the bullseye. So let's walk through it. Step 1, you shoot your arrow. That's the forward pass. And you miss. That's okay. Step 2, you measure how much you missed by. Maybe it was 10 inches to the left. That's your error. Now here comes the magic. Step 3, you work backward. You ask, okay, why did I miss? Well, my release was a bit early. Why was my release early? Because my elbow was too high. Why was my elbow high? Because my stance was a little too wide. You trace the blame backward, from the result all the way back to the start. Then, step 4, you adjust everything just a tiny bit and you shoot again. And this time, you're a little closer. Okay, so let's connect that back to our animal shelter network. Adjusting your stance and your elbow in the network is the exact same thing as slightly changing the weights on all those connections. The network literally goes back and tweaks every single weight just a tiny, tiny bit in a way that would have made its last guess just a little bit better. And here's the kicker. It doesn't do this just one time. This whole cycle, make a guess, measure how wrong it was, and then make thousands of tiny adjustments, it repeats that over and over and over again. Thousands, even millions of times. And with every single pass, it gets just a little bit smarter, a little more accurate. So let's just recap the crucial points here. 1, neural networks are inspired by our brains, but they really just run on math. 2, they're built from simple layers of nodes connected by those all-important weights. 3, when the network makes a guess, we call that a forward pass. And 4, when it learns from a wrong guess by adjusting its weights, that's backpropagation. And that right there is the essence of how a machine learns. And that really leaves us with a pretty incredible thought, doesn't it? I mean, the same basic process we just used to teach a machine to recognize a rabbit, if you just scale it up, more data, bigger networks, that exact same principle is how AI learns to compose music, to help doctors diagnose diseases, even to drive a car. It's all just guess, measure the error, and adjust over and over again. So it makes you wonder, right? What should we teach it to understand next?